What is calculus? In simple terms, calculus is the mathematical language that describes change, whether it is change in distance or in area. Calculus is used widely in many different areas of physics and even astronomy. Astronomers use calculus to study the different motions of planets, meteorites, and spaceships. One example of how calculus is applied in astronomy is the introduction of Kepler's second law of planetary motion, vector calculus, and force of gravity. Kepler's second law says that a planet shifts out equal areas in equal times, that is, the area divided by time, called the areal velocity, is constant. Based on the figure below, the time it takes a planet to move from position A to B, sweeping out area A1, is exactly the time taken to move from position C to D, sweeping area A2, and to move from E to F, sweeping out area A3. These areas are the same. Using the law of conservation of angular momentum, the law can be verified. At any point of time, the angular momentum can be given as L is equal to m times r times 2 omega. Now consider a small area delta A described in a small time interval delta t. The covered angle is delta theta. Let the radius of curvature of the path be r. Then the length of the arc covered is equal to the equation below. Therefore, delta A over delta t is equal to bracket 1 over 2 times r squared times delta theta over delta t. Taking limit both sides as delta t is limit equal to 0, then the equation will be shown as below. Now, by conservation of angular momentum, L is a constant. Thus, delta A over delta t is equal to constant. The area swept in equal interval of time is a constant. Kepler's second law also can be stated as the aerial velocity of a planet revolving around the Sun in elliptical orbit remains constant, which implies the angular momentum of a planet remains constant. As the angular momentum is constant, as all planetary motions are planar motions, which is a direct consequence of central force.
Another part is application in astronomy for the rocket in calculus. Rocket has included differentiation to move out the rocket to the planet. For example, we are assuming the rocket arrays orbits. Acceleration of a rocket at the moment the value have finished the speed is z equal to 1000 power of g over x. The mass of the rocket is k equal to 6000 kg and the power rate is y equal to 500 power of kg over x. We assume the equation for rocket is s equal to y log k power of 0 over k. The rocket speed is v and the rocket mass is k of h, but the power rate is constant. So we have the equation like this: k of h equal to k power of 0 minus yh. Supposing the finished speed is constant, the rocket for equation is s of h equal to z log k power of 0 divided by k power of 0 minus yh. Acceleration for the rocket by differentiating with respect to h, ds over dh equal to z power 1 times 1 over k power of 0 divided by k power of 0 minus yh times the negative k power of 0 of x minus y divided by k power of 0 minus yh power of 2 equal to z times k power of 0 minus yh. The rocket for the acceleration for equation is a of h equal to zy divided by k power of 0 minus yh. Addition as a is the speed which are time h over rate y and mean speed z. The partial derivative h is represented each way like this: a over h equal to zy k power of 0 minus yh power of 2x negative y equal to zy power of 2 divided by k power of 0 minus yh. So it can greater than the 0. The partial derivatives is run like this: a over hash equal to negative z times vk power 0 minus y hash minus z y times negative hash divided by k power 0 minus y hash power of 2 equal to z k power of 0 divided by k power 0 minus y hash power of 2 is as greater than the 0. Thus, the differential for the origin of it is a equal to z k divided by k power 0 minus y hash, so we can get the answer is rounded to 83 gram. In addition, we move on another example which integration on the Jupiter. For assuming there is a spin scale with 1 kg mass on Jupiter, the force is 4.2 N, on Earth the force is 6.5 N. Obtaining the value of force equal to mass times acceleration, so it will be like this equation: 4.2 N over S power of 2 is A. The equation becomes 4.2 M over S over 1 second equal to 1 mph over 1 second because the acceleration is equal by the gravity on Jupiter. As the hash equal to 1 second, V equal to 1.5 mph, assume that the hash O equal to 6 and the V equal to 9 mph. We can get A of hash equal to 4.2 M over S power of 2, VH integrate 4.2 plus C power of 1 d hash, and Y hash integrate 4.2 plus C1 dt for the 4.2 T power of 2 plus C1 plus C2 for the mass. Assuming the Jupiter we have the total building that is 60 meters, we can calculate that 60 equal to 4.2 T power of 2 divided by 2 equal to 120 divided by 4.2 equal to T power of 2. So the answer is 9.3 S equal to T, and then the convert to 28.57. However, we have the building that 60 meters equal to 6.5 T power 2 divided by 2 equal to 120 divided by 6.5, so the answer is 4.3 S equal to T. That's all for us or our group. Thank you for your watching.